Welcome back. So now that we have done some little bit of manipulation and cleaning on the original dataset, let's pick up where we left off and try to see if we can do any serious data exploration, any statistical analysis on the dataset. So as usual, let's import the pandas library and the plotting library, which is matplotlib, and run the cell to import them. Now, as usual, at the end of the last notebook, you must have seen that we had written this data to this particular path. We had a folder called data within which we created this file Kaggle clean, and we're just going to read it back again and look at the first 5 rows of that data set. So you see, we still have the same problem. That is, our first column is still text and our header is obviously already text. So there's our data is still not completely numerical. If we were to again take the histogram of all the durations in this data set, we'd still run into the same problem where it'll say that, it can't compare these value against a particular string. And that is why we essentially have to figure out a way to drop this entire row and see where we can include that data, so that only we are only restricted to crunching the data that is present in rows 1 onwards. So let's see what we can do to that. Now, one of the arguments that the read CSV function accepts is something called a header. Now, by default, if you don't provide that argument, when we read the data for the first time using the read CSV function, we did not tell it what its header was supposed to be. So usually it simply takes the first row as the header. It assumes that there is a header and the first row is the header. If there is no header, then you explicitly have to tell it that there is no header. But of course, in this particular case, our header is not just one column, it's actually two columns. You see that this row is actually a header, but it has started coming in as the first column. So what we're doing here is we're telling it that take the 0th row as the header and also take the first row as the header. So basically our header should span 2 rows. So let's do that and see what it shows us again. There we have. You see that now our header is spanning this row and the first row as well. And now the data starts correctly coming in from the 0th row onwards. But at the same time, you see that our header has grown a little complicated. For example, earlier when I wanted to refer to this particular column, I just used call name as the string, time from start to finish in seconds. And I use that call name to access the data. As you know, I can just put the name of a column within a square brackets and call it on the data frame to get a particular column out of the data frame. But here, since my data frame has gotten a little complicated because of the header, I don't know what to do with this extra text. So here's one way to do it. If we simply look at the columns, here's what it's going to give me. It basically tells me that it's a multi-index instead of a single index as we have seen earlier. What a multi-index means is that the data is being indexed by two values, not one value. So essentially, earlier we had rows or rather columns which were indexed just by this particular header. Now we have columns which are being indexed by two headers at a time, not one header, right? So that's what a multi-index means. It basically says that time from start to finish is also a descriptor, as well as duration in seconds is also another descriptor, right? So if you look at the first column, which is basically Q1, this was the 0th column. If you look at the first column, which is Q1, it will basically give me this data set. Now you see that this is not a single column. It's basically creating another column which has a column within itself. And that is basically the second header. So it's sort of a hierarchy. You see that Q1 is basically the top level column, and under that there is another column. So that's how it's interpreting that. And if we were actually to pick those two columns together, then it would give me the raw column itself completely. And if you look at the name of this column, you see that it's giving us a tuple. From the first video that we saw on Python, we know that tuple is basically one of the data structures, and it says that this tuple has two elements. One is Q1 and the second is what is your age in years. And that actually matches this. We see that Q1 and what is your age in years are basically two different column headers, and both of them here are required to refer to the same data. This is very complicated. So what we are going to do is try and make it more manageable. We are going to keep only the first level of indexing on the data frame, and the second we are going to keep only for reference. So basically what we are going to do is we are going to tell pandas that only consider this particular row as the header, and this we are going to basically delete, but we are going to keep it separately somewhere so that later if we forget what Q6 is, we can always look it up in a particular lookup table or a dictionary where we can say that, okay, I might have forgotten what Q6 is, but this is what it means. Q6 corresponds to the question which asks what is the size of the company where you are employed. So in order to keep accessing the data, we are simply going to keep these codes, but their meanings we are going to throw away from the table, but maintain in a separate dictionary somewhere. So let's try and do that. So basically, one quick way to do that is use something called a dictionary comprehension. As we know, we can create dictionaries by using something like this. Sorry. Yeah. So as you know, we can create dictionaries using a pair of braces, and I can say something like this is my key and my value. And then I have another key and another value, something like that. So that basically creates my dictionary. One quick way to create a dictionary is using something called a dictionary comprehension. So what it's going to do is essentially you keep the braces as they are, but inside, instead of writing a set of key value pairs, now of course we can't write the whole set of 246 key value pairs as are present here. What we want essentially is a dictionary where the question codes are my keys and the text of the question is the value. So I can just put the question code in that dictionary and get the question corresponding to that code. That's the kind of dictionary I want. One quick way to do that is to use a dictionary comprehension, where I say that k colon v for k comma v in df.columns. Now df.columns, since it is a multi-index, is going to iterate over both these lists. The first level, which is the question code, and the second level, which is the question text. So k becomes my question code and v becomes my question text, and that gives me this whole dictionary. It basically is a massive Python dictionary which says that q1 is a key which corresponds to what is your age, q2 is a key which corresponds to what is your gender, q4 is the question which corresponds to what is the highest level of formal education that you have, and so on, right? So let's scroll all the way down. It's going to be pretty large because there are, well, 246 questions. Much easier way is to simply use the dict function. Remember that just like we use the list function to create lists, you can use the dict function to create dictionaries. And you can simply call this on df.columns. df.columns is simply a multi-index column, which means that it has key values everywhere. And we do that, we basically get the same data again, right? So this is an easier way to do it rather than using dictionary comprehensions. Of course, one of them might be suitable for a certain application, and you should be aware of what both of them do. So now, since we know which codes corresponds to which question, we can get rid of the second level of columns. So what we're going to do is create a new dictionary called question codes, and that is essentially this particular dictionary. You have the keys as the question codes and the values as the text of the question, and that creates my question codes. And after that, I'm going to create a new data frame, which I'll be calling xdf, simply as a modification of my original data frame. And I'm going to say that drop level. So drop level is a function which tells pandas to drop a level of index from the data set. If we go all the way back to our data frame, there's actually a lot of text here. What we can do is simply remove this. So I can say clear output, and here too I can say clear output. So we have a little more room to scroll around now. If we go back to the data, we see that my header is present in two levels. This is the first level and this is the second level. Now, obviously that means that this is the 0th level and this is the first level. So what I'm going to simply do is ask pandas to drop the first level along the first axis. Remember, we have seen that when we talk of the 0th axis, we are talking about row-wise stuff, whereas when we talk about the first axis, we are talking about the column-wise stuff. Here, our second level of indexing is happening along the columns, not along the rows. Remember that the rows are still indexed with a single number. So we are simply going to drop that first thing, and there it is. Now, when we look at xdf.head, we have a lot cleaner data set. We just have the question codes and we have the values. But of course, now how do I find out what Q1 means? Well, I've already created a dictionary called question codes, right? And there I can just put in Q1 and I say that, okay, Q1 does correspond to what is your age. And then Q2 also correspondingly corresponds to this question, what is your gender? So there it is. We have colon Q2, which corresponds to gender. And here's an exercise. How would we find the gender ratio of this survey? So pause the video for a while, take a minute to think about it and do the exercise. We already know how to get a particular column out of pandas. We just do df square brackets, put in the name of the column, that gives you the whole column. So one of the things we might want to do simply is to calculate all the males and females and find their ratio essentially. So essentially the point is counting how many males are there, counting how many females are there. There could be other genders also, so be aware of that and see what are the proportions of different genders. So feel free to look around, feel free to Google, and here we are going to introduce some of the more advanced pandas functionality, and we'll do that as soon as we resume. So let's take a shot at how we would do this. In order to find the gender ratio, that is in what proportion the different genders are present, first of all, I have to find out what all different values are there. So male and female I can already see here, but note that I am looking at I am looking at only 5 rows out of the 19,718 rows. So let's say that we want to find out all the possible values that people have put in under Q2, which is gender. So let's say that we create an empty list called gender, and then we are going to iterate through this row. So what I can do then is for gender in df q2, which is genders. By the way, dot values is what actually lets you iterate through the values. That's essentially the list, which is the underlying data structure of a particular column. And I'm going to say that if gender is already in genders, remember that in is something we use to check membership in a list. So this is a list which is currently empty, and we are going to keep on accumulating the different genders that we see. So if the gender that we have in a particular row of Q2 is already in this list, then we do nothing, which means continue the iteration. Or then if it is not inside the gender, then we can simply do genders dot append of gender. So we are going to keep on appending to this dictionary, and at the end we are just going to say print genders. So again, to take a look at this in a little more detail, we have created an empty list which contains all the genders in that data set, and we are going to iterate through that column, and we say that if the gender that is in a particular iteration is already present in my list, if gender in genders, then I simply continue, I don't do anything. But if it is not there, then I'm simply going to append that gender to my genders, and then at the end, once the for loop is done, I'm going to print out the list of all the accumulated genders. So there it is. So we see that we have 4 things. We have something like there is male, there is female, there is one option that says prefer to self-describe, and the other one says prefer not to say. Now, one easy way of doing that is instead of all of this for loop jugglery, I can simply do df q2, which is my column, and I can simply do a unique statement on it. Well, same data frame attribute. Oh, of course, we had xdf, not simply df, because xdf was something that we created after dropping the first level of hierarchy. So let's do it on xdf, and there it is. So we get the same 4 values back again, this time without using the for loop. So this is a method that is already built into pandas. Use it whenever you can. Whenever you find yourself writing too much extra code, that's probably a good signal that you might just want to look up in the documentation and try to find something that does the job for you ready-made. So there it is. These are all the unique genders. Now the next thing that we have to do is basically count how many males are there, how many females are there, how many people prefer to self-describe, and how many people prefer not to say. So what we are going to do is simply create a list of counts, and let us say that I create a dictionary called counts, where I say male is 0, female is 0, prefer to self-describe is a key again, which is 0, and prefer not to say is yet another key which has a value of 0. Now what I'm going to do is again iterate through this list. So let's say for gender in xdf of q2.values, I'm just going to say my count is basically from the counts, I'm just going to get the gender. Now I know that this value of gender is going to be one of the keys present here. It can't be a 5th key because I already know what are all the unique values that I have, and those are the ones that I've put in this dictionary. Now since counts is my dictionary and gender is one of the values in the row, whenever I get this, initially it's going to be 0, And since I have found that particular gender, I'm just going to increment my count. So I'm just going to take whatever value is already accumulated there and add 1 to it. And then I'm going to put that value back into the dictionary. So essentially this is getting the count access, this step increments the count, and this step steps back the count, adds the count back to the dictionary. And then I say print counts. So there we are. We have 15,890 males, 3,178 males, 48 people prefer to self-describe, and 303 people prefer not to say. So that's basically the total number of all types of genders that we have. One quick way to simply get the ratio is divide each of these values by the total number of rows that are present. And like we know, the total number of rows that are present can be obtained by saying xdf.shape, where 19419 is basically the number of filtered rows and 246 is still the number of columns. So I have something like in rows, note that this is a tuple and the first value in the tuple is going to be the number of rows. So I can say n rows equal to xdf.shape of 0, because that gets me the 0th element of the tuple. And then I'm going to say that for gender and count, that's probably a bad idea. We don't want to iterate over a dictionary and then do it again. So at the end of it, what we could simply do is for gender count in counts.items, print gender, and then what we're going to do is divide count by the number of rows, multiply it by 100, and say that that's my percentage. Basically, this is the percentage for a given gender. So let's run that. And now we know that 81% are males, 16% are females, 0.24% prefer to self-describe, and 1.5% prefer not to say. Now again, here, as far as possible, we would like to avoid all of this jugglery again. So one quick way to avoid this is basically just to do something like this. I simply take XDF, I select the column that I'm interested in, and I use a new method called value underscore counts. What it's going to do is it's simply going to count each value. So there it is. And we have the same things again and again. We have the male, which occurs 15,890 times, females occur 3,178 times, prefer not to say comes 303 times, and those who prefer to self-describe are 48 in number. Now, one quick way to convert this into a percentage is to divide that by n rows, which we have already calculated as xdf.shape of 0, and multiplied by 100, and that gives me the same percentages that I earlier calculated. So what we see here is an example of how you can just use one line of pandas code to counter something like 8 lines of pure Python code. Now another interesting thing is that you can, since these are percentages, they all add up to 100%, we can use something like a pie chart to plot this. So in order to do that, remember that this is a pandas series, and pandas series and data frames both support excellent data visualization and plotting capabilities. So I can just do something like this: plot, and I say kind is pi, and there we are. So we have the male, we have the females, and the minuscule proportions of people who say that they prefer to self-describe or prefer not to say. So this is one quick way to see what sort of proportions you have in your data. You basically use value counts, you can convert it into a percentage and then plot it as a pie chart. You can of course plot it as a bunch of other things also. We can also plot it as a bar chart. But ultimately the bar chart doesn't exactly apply here because we are looking at proportions, so part of whole. So that's why the pie chart might make sense. A lot of data visualization experts hate pie charts for good reason. There are always good or bad places to use certain kinds of charts. So be careful with what visualization you pick for what kind of a problem. In this case, it works. So there it is. One easy way to look at different unique values and to summarize them is by looking at different how many times each value occurs and convert it into percentages. However, this only works if the number of unique values is very small. Remember that we had only 4 unique values here in about 19,000 rows. If we had something like 5,000 unique values in 19,000 rows, then this pie chart would have looked like it has too many spokes. So we don't want that either. So make sure that before you start doing an analysis of this kind, the number of unique values that you have is fairly small. One quick way to simply check the number of unique values, not the unique values themselves, is to take the column, which we do like this, and call n unique on it. Earlier we called unique to get the unique values themselves. We can call n unique to get the number of unique values. And we know that though there are 4 unique values over here, male, female, prefer to self-describe and prefer not to say, right? So there we are. One quick way to get a bunch of different summary statistics or univariate statistics, as we have studied before, for a given column is to use the describe function that is provided for every column in a pandas data frame. So when I say I just want to do q2.describe, here it is. It straight away tells me that the count is 19,419. There are 4 unique values. The most frequent is male, which has a frequency of this much. So we know that males occurred 81% of the times, and that corresponds to, out of 19,490, 15,890. Of course, remember that Q2 was a categorical column. We have already covered what are numerical, ordinal, and categorical columns. Q2 was a categorical column, therefore its descriptive statistics are going to be different than, say, the descriptive statistics of a numerical column. Now, the only numerical column we have in our data set is time from start to finish. So let's try to see what describe would tell us if I try to do a describe on that. So let's say I do an XDF and then I put in time from start to finish and then do a describe. So here you see it gives me a very different set of statistics because it's a numerical column. Of course, count is still valid over here, but now it has a mean, a standard deviation, it has a minimum value. Of course, you see that the minimum value is 60 because we had already cleaned the data in the previous video. Then 25%, 50% and 75%, these are essentially the percentile. What this means is that 25% of all values are below 350, 50% of them are below 547 and 75% of them are below 942, and the maximum value is 8,43,612 seconds. No idea what this guy was doing, but the bigger point that we're trying to make here is that the output of describe is different for different types of columns. For numerical columns, it's going to give me summary statistics. For categorical column, also it's going to give me some summary statistics, but those statistics themselves are going to be different. So these were some examples of univariate data analysis. Let's take a look at how we can perform a little bit of bivariate data analysis as well. Now, specifically, we have created a data set which is clean and we have the header columns properly formatted. Let's take a look at the Indian subset of the data. As you remember, we have a dictionary called question codes, which maps the question code to the actual question. So let's take a look at what Q3 is. And we say that, question Q3 corresponds to country of residence. So what we're going to do is take that subset of the data, which corresponds to all the Indian respondents. If you remember from the previous exercise, we had performed filtering on the data set which contained marks and attempts of multiple students for a person called Emily. So here we are going to apply the same syntax. We are going to select the column Q3, which is country of residence. We are going to compare it with the string India, and that's going to return a bunch of true and false values. And those true and false values are what we are going to use to pick the rows which correspond to Indian respondents out of the XDF data frame. And that subset of the data we are going to create into another variable which we'll just call India. And then let's simply do India.head. And there we are. We see that the first respondent is from India, the fourth is from India, the sixth is from India, the 10th is from India, and so on. So we again are looking at just 5 rows because we have done a head and 246 columns. So these are all, Indian respondents. So let's take a look at what kind of salaries Kaggle users, Indian Kaggle users, are earning in India. So let's take a look at Q10, which is the question corresponding to salary. What is your current yearly compensation in approximate US dollars? So let's take a look at what this data looks like. Head, and basically you see that it gives us a lot of values. It's basically not single values but ranges of values. The first respondent is saying that their yearly compensation in approximate US dollars is $5,000 to something like $7,499. The fourth respondent is saying that their approximate compensation in American dollars is from $4,000 to $5,000 and so on. We also have some NaN values. NaN here means not a number, which means that that was a null value. This particular respondent, respondent number 10, chose not to answer this question perhaps. So that is why their response for this field is not number. It's basically not applicable, it's a null value. Now, one way to simply calculate how many null values are present in a row is by using this function called isAny. Basically, select the column that you want and apply the isAny function. When we run that, we see that a bunch of things are true. So this is true because the 10th respondent's compensation is not a number. The 14th one's response is also not a number, and so on. So you see that there are a lot of values here which are true, which means that a lot of Indians didn't exactly reveal the approximate salary that they earn in US dollars. So first, what we need to do is, if we have to do an exploration on salaries, we have to drop these rows. We have to make sure that we only take those people whose yearly compensation, at least in the broad range, is known. We want to drop everything that has a NaN under this particular column. Now, to see how many people have these null values, we can just add a dot sum in front of the isAny. So essentially, we take the isAny, which is going to return this true and false values for each row, and when we sum them up, we are basically going to get the number of people who haven't responded to this question. So let's run that, and we say that overall number of people who did not respond to this question is 2,252, and the total length of the Indian subset of the data is 4,729. So, a little less than half the people have basically not answered this question. And what we need to do is drop all the rows which have NA in this particular column, NaN in this particular column. And for that, we can use a function called drop NA, which means drop not a number values. And we say that only use the Q10 column as a subset, in the sense that we are saying that from the India data frame, drop all those rows for which Q10 is a null. And we want to do this again in place as earlier. We don't want to create a new data frame. We want to modify the existing data frame in place. And then when we take the head again of the India data set, this is what we get. So you see that now we are not seeing any null values. But at the same time, we see that some rows have a dollar sign in front of them. You see that this particular row doesn't have a dollar, this particular row doesn't have a dollar, but this one does. So one of the things that we need to do in order to perform any sort of mathematical analysis is get rid of that dollar symbol and see if we can only focus on the numbers itself. So we have seen lambda functions before. Basically, it's just a one-line function which takes an input and performs some operation on that input. So basically, we are creating a lambda function called remove dollar, which takes an input x, and in that x, it's going to replace the dollar with an empty string. It's basically just going to remove that dollar. Then on this subset, the India subset, we take the Q10 column, which corresponds to compensation, and we are going to apply the remove dollar function. What this will do is that for every row, this row, and all the rows, all the 4,729 minus 2252 rows that we've already dropped on that many number of rows, it's going to apply the remove dollar function. So when we do that and run this again, we see that this time we get something which doesn't have a dollar. So we see that the 22nd respondent had dollar in front of their output. Here the dollar is gone, right? Now another thing we need to do, further step in the pre-processing, is to remove the commas, because that comma is going to prevent us from interpreting these figures as numbers. So the moment you put in a comma, Python will not be able to convert that into a number, and therefore it will still treat the whole thing as a string instead of as a number. But in order to do statistics, we need numbers. So that's why, just like we've removed the dollar symbol first, now we are going to remove the comma. Another alternative to use this particular lambda function is to use the str.replace function that is also available on any pandas column. So it's simply going to say that take this particular column, and within that, wherever you find a comma, replace it with an empty string. It's just like the lambda, except it's one line less than this, as you can see. So let's do that, and then when we see the head, we see that there are no commas. 5 comma 000 dash 7 comma 499 has become 5000 hyphen 7499. So if we were to basically take this value, we can interpret that as a number. We can call the int function, which we have seen before, to convert this into an integer. Now, the next big problem that we have in cleaning and pre-processing the data is that these are not single numbers. These are ranges of numbers. So what we need to do is separate out this column. Basically, we have a salary column. We need a salary minimum, which is going to contain the lower bound, 5,000, 4,000, 10,000, 0, 100,000, and so on as the minimum range of the values, the lower bucket or the lower edge. And then we need another column which contains 7499, 4999, 14999, and so on, which is the upper edge of that particular range. So what we're going to do is, just like we had a str.replace, we also have an str.split. And here what the split function does is that it takes in any string and it's going to split every row on that string if that string is found. So here the splitter that we are using is a hyphen. So essentially what it's going to do is, every time it sees a hyphen, it's going to take everything before it and create a separate element out of it, and then it's going to take everything after it and create a separate element out of that. So let's try that. So that's how we see it. It's basically going to split on whatever splitter we provide, and the remaining parts, it's basically going to convert into a list. So 5000-7499 became a list which contains 5000 as the first element and 7499 as the second element, and the same process has been carried over for the entire range. So let's try that. So in order to keep this data as a new column in our data frame, we are going to create a new column called salary range, and that we are going to simply assign to this particular function. We are going to take a column and call str.split. We are simply going to create a new column called salary range, which takes the Q10 column and calls the str.split with the hyphen as the delimiter, the splitter. So let's do that, and when we look at the head of this function, this is what we get. So now this is present as a new column in the India data frame itself. So now what we need to do is get the min and maximum salaries from this range. So for example, here the minimum salary is 5,000, the maximum salary is 7499. Now that also we can be doing with a lambda function. Essentially, remember that this is a list, and what we are going to do is apply a lambda function which takes the 0th element of the list and then takes the first element of the list. Now we know that 0th element of the list is the minimum salary, so we simply call it smin, and the first element of the list is basically smax, which is the upper bound of the salary. So let's run that, and we see that something has failed. It's basically said that the list index is out of range. What has gone wrong here? Let's take a look. These are the reasons why it might have gone wrong. First is that we didn't write the code properly, which would have resulted in incorrect syntax, but that doesn't seem to be the problem because it has given me a specific index error. If it was a syntax error, it would have said that it's a syntax error. There might be something like missing values in the column. That is also not the case because we have already dropped all the missing values when we did the drop any, right? Then the third option is that not all rows have two elements in the salary range column. Now you see that in order for this lambda to work, I need the 0th element as well as I need the first element. And if you look at this particular error carefully, you see that it has failed at the second part. That's what the arrow is showing. So this particular function ran perfectly fine, which means that after the split is done, it is able to find the 0th element all the time. But in some cases, it's not able to find the first element. The only reason that can happen is that the string contains only one element. Some cases, it just doesn't contain anything. So let's see what happens to those cases where the string did not contain two elements. Well, now we know that the salary range column, each row is basically a list. Earlier, each row was a string, which we have converted into a list by carrying out the split function. So basically each row is going to be a list now. And we know how to calculate the length of a list. We can just do len and the list. So what we are going to do is apply the length function to this, and we are going to capture the output in L. And when we see the minimum length of the lists that are available, so this has a length of 2, this has a length of 2, all of these have a length of 2, right? So we would expect throughout the data frame for every list within the salary range column to have a length of 2, right? But that's not what is happening. If we look at the minimum of list, we see that there are definitely some lists which have a length of only 1. Now let's see why this happened. One of the reasons why that could happen is like that. Let's see. You see that we have this data set where the salary range is simply greater than 5,000 and the S-min is simply greater than 5,000. Now you see that these are rows which don't contain a hyphen at all. We were counting on that hyphen to be able to split the minimum salary and the maximum salary. But if there is no hyphen, if your salary is actually more than 500,000 US dollars, then there is no such thing as a range. There isn't like a minimum hyphen maximum. There's just greater than 5,000, right? So that is why we did not end up with a minimum value at all. So in order to get the maximum salary, we already have the minimum salary, which is simply our S-min. Now, in order to get the maximum salary, what we have to do is modify our lambda function a little bit. So now this is the function that failed. It simply said that get the first value, which is this particular value out of it. Now, of course, some of them didn't have the hyphen at all. So, it might have ended up with a list with a single element in it. So there was no first element. There was only the 0th element. So what we are going to do is modify the lambda function such that we say that if the length of x is 2, then give us x1. Otherwise, give us the 0th value. So let's do that, and then we have S-min, X-max. This time it ran properly. By the way, these things that you keep seeing, these are just warnings. They are not errors, and that's okay. It's okay to ignore them for now. And then when we look at S-min, these are now the individual objects that we see, and these are pure numbers. They are still objects, but they are at least able to be converted into numbers. We can just do an as type int as we did earlier, and then convert them into numbers. Whereas you see in the max column again, we'll still have this greater than 5,000 cell. So greater than 500,000. Now what we need to do is get rid of that greater than 5,000 and cap it there. Now if it's greater than 500,000, we don't know how large it can go. So let's just use whatever we have. Let's use the upper bound as the maximum salary itself. And what we're going to do then is simply replace again. Like earlier, we replace the dollar or the comma, we replace the greater than sign with an empty string. And so there it is. Now we have an S-min. Let's take a look at the salary range, the salary min, and the salary max columns. And there we are. So we have the salary range, which we computed by splitting. 5,000 becomes the minimum salary, and 7,499 becomes the maximum salary. Let's also take a look at the bottom few rows. Just like head shows the top 5 rows, tail shows the bottom 5 rows. So there it is. You see 0 is the minimum salary, 999 is the first salary. So minimum maximum becomes a little bit like that. Now let's see if we can convert the S-min column here into integers. For that we can use the as type int. And as earlier, we can simply use the hist function to check the histogram. So now we have managed to get a numerical column out of a bunch of categorical columns. So let's run that. And this is what we see. We see that most people have a salary of less than, 50,000 US dollars. So basically that makes sense. And very few people have salaries that are more than 50,000 US dollars. Some of them have all the way up to 500,000. So there are definitely the disparity. You see that there is a lot of room at the, there is a lot of crowd at the bottom. A lot of people are earning less than $50,000 per year. Well, by Indian standards, that may be a good amount of money. But remember that there are still a bunch of people far ahead of that particular curve. Now, in order to see this a little more, in detail, we simply increase the number of bins. This is 10 by default, and we are just going to increase it by the bins to 50, and we are going to limit our x-axis to 0 and 100,000. So basically our x-axis goes all the way from 0 to 500,000. We just want to, since most of our data is concentrated in this particular bin, we are setting the x limit. So this is what the set xlim function does. It basically sets the x limit to between 0 and 100,000, and then we're also changing the number of bins. So there we are. So this is basically how it looks like. Most of the data, as we saw, is concentrated between these two bins. But if we magnify that particular limit and increase the number of bins, this is what we see again. So most people, again, like roughly 1400 people, are earning less than or equal to $10,000 per annum, and fewer and fewer people keep on getting higher salaries, and that makes sense. This is also called a Pareto distribution or a power law distribution, where most people will be earning lower salaries, and as the salaries goes on increasing, more and more people start, fewer and fewer people rather start earning those higher amounts of salary, right? So then how do we examine some other non-numerical columns? Remember that this is still univariate analysis. Let's take a look at one other non-numerical column or a categorical column, Q5, which is select the title which is most similar to your current role. This is basically your designation or your job choice or your job title. And let's take a look. So we have things like software engineer, other, business analyst, data scientist, software engineer, and so on. If you look at the value counts, we see that there are these many unique designations within the Indian data set. Most frequently, the ones that are occurred are software engineer and data scientists. Of course, this being data from Kaggle, which is a platform primarily for data scientists, it's not surprising that a lot of people show up here. What is surprising though is there are more than 600 data scientists, there are more than 600 software engineers, but there are only 300 data analysts. So what this means is that perhaps data analyst is not a very popular job title amongst people. Other is just sort of a catch-all term for any other job title that you may have, which doesn't fall into any of the other categories. There are very few database engineers and administrators. That's not surprising. Now, if I wanted to see the proportion of all of these, one of the quick ways I could do that is, you've seen that we have a plot function and we used it to plot a bar chart and a pie chart before. So we're just going to plot the bar chart again on this particular value counts output. So there it is. Basically, it tells me that there are about 600 odd data scientists and data engineers, but half of them, in fact, it's really weird that the top two most frequently occurring designations are data scientists and software engineers, and the second designation and the third most frequent designation that occurs is almost half of the first two, which is weird. Usually you'll see some sort of a smooth curve over here, but this is interesting. That's kind of an anomaly. This means that Kaggle in India is more or less completely dominated by data scientists and software engineers. Now you see this isn't very readable, so you can also plot a bar edge, which is a horizontal bar chart. That creates something like this. So this is slightly more readable because you can read the titles, and the length of the bars anyway indicate the proportion in which they are present. So these are two independent kinds of univariate analysis we have done. We took a numerical column. Well, we manufactured first a numerical column, we saw its histogram, we saw what the behavior of salaries is, and then we simply did counting on a categorical column and saw the proportion of them. But here's an example of a bivariate analysis, which I will start as an exercise. Which job title has the highest average salary? So think about this. How are we going to do this? Basically, we want to say that get all the data scientists, compute their salaries, get the average. Get all the software engineers, compute the average salary and report it. And that's what we want to do for every job title. And then we want to figure out which job title has the highest average salary. Now, of course, what do we mean by salary? We in fact have two columns. We had S min and S max. So which of them do we consider as the salary? Well, let's take S min, because that way we are, preparing an analysis for the worst possible scenario. That is, if we find a reasonable output, even by considering S min, then we know that even if you are at the lower edge of whatever you could be earning, it's still a good outlook. So let's simply take S min as the salary. S max is a little optimistic. Let's go with, the very conservative or the worst case possible approach over here. So let's say that SMIN is the actual salary that you're earning. And then we want to figure out, given that SMIN is the salary, which particular job title has the most, has the highest average salary. And now what do we mean by average again then is that to reiterate, we pick a particular title, let's say data scientist, find all the data scientists in that particular data frame, calculate the average of all their salaries, which is SMIN, and then find out which of these particular roles has the highest average. So think about this, try to break it down into smaller steps, and then we'll see about how to solve this. Feel free to pause the video, look around, and come back when you have a solution. Well, let's get started and see how we can basically break this down. Well, one of the first thing we need to do is capture in some variable all of the different job titles that we already have. We can do that straight away by looking at this variable. So there it is. These are all the different titles we have and these are their counts. So let's just call it this job. Let's call this particular variable job title counts equal to the value counts of the Q5 column. So then job title counts, this is what it looks like. Then what I need to do is filter the original data set by each of these values, take the SMIN value out of them, sum them up and basically divide it by this number because that's the number of times it appears. So that would then give me the average. So what I can do is I want to iterate over this value. Now one of the things about iterating over a particular series is that remember that it basically behaves like a dictionary. So it would be something like for job title, which is the key, and then count, which is the value in job title counts dot iter items, and I can just do print job title and count just to ensure that my iteration is happening properly, and it seems like it is. I have the job title and I have the count against it. So my job title and count variables are in the iterative loop are working correctly as expected. So what I can do is create a small df, which is something like I take xdf and then I take the Q5 column such that it matches this particular job title. So basically I have the small df, which is a subset of the, oh sorry, this should not be xdf, this should be India. So out of the India slice of the data set, we want to take the fifth column and filter it with the particular job title. And we are of course iterating on all of them. So that small df, and let's just break this loop over here to find out if we are actually doing this iteration correctly. So what break does is that after just one step of iteration, it's just going to break. Okay, so let's do that. And let's take a look at small df.head. Nothing special, but you see that Q5 is basically data scientist, and that makes sense. The first item was data scientist. It just took, the data scientist in the first level of iteration and broke the data set. So this is my data frame for all the people who have the designation of a data scientist. Now what I'm going to do is simply pick the salary column, which is small df, and then I can do just SMIN because earlier, as we decided, we are going to use SMIN as the salary. And then I'm just going to do a salary dot sum. You remember that's how you do a salary. But let's break it anyway and see if we can get the salary column properly. So if you look at salary, here's what we get. So basically the sixth person in the data set has a salary of 10,000. The 76th person has a salary of 20,000 and so on. Some people have 5,000, some people have 4,000 and so on. I can just do a salary dot sum to get the totals. Oh, that didn't work. You see, I wanted to basically do sum of the salary, but it all, got converted into a big string, which means that the salaries that we're looking at are not basically integers. When I do a salary dot head, it basically says that the data type is object. Well, in that case, let's just do a salary dot as type integer, which is fine. And then when I do a sum, gives me something, which is a number, which is not that crazy string that it gave me earlier. What it did earlier was that it simply concatenated all the strings, which is why I was getting a big string. So when you do a sum on a column that contains string, it's going to concatenate the strings. It's not going to produce the numerical result, even if the string actually represents a number. That is simply because we haven't done this as type integer step. So there it is. I can simply add this over here. I can do something like as type integer, and then I can say total salary for title is salary dot sum, and then I can say average salary for title is equal to, well, total salary for title divided by the count, because counts I'm getting from here anyway, right? That becomes my average salary. Now, in order to contain all this data, I'll create a dictionary. Let's just call it salaries, which is an empty dictionary. What I'm going to do is that I'm going to put the designation inside the dictionary, which is job title, and the value is going to be the average salary for the title. So let's run this and print what we get in salaries. There is a name error. It says that salary is not defined. Well, it's not salary, it's salaries. So there it is. We have corrected the name, and we see that the average salary of a data scientist in India is $23,000. That of a software engineer is much lower, which is $13,000. That of a data analyst is, well, surprisingly less than that of a software engineer, which is $13,375. It's a difference of $500 per year, which is still a sizable amount. And there is the other field which has a high salary, but then the other, it's just a collection of whatever fields didn't already occur there. Now you see that this is basically a dictionary. One of the things I could simply do is put that dictionary back into a series and plot it as a bar chart again. So there it is. So we see that product managers and project managers earn the most, followed by data scientists, followed by research scientists, followed by business analysts, followed by statisticians, and so on. So that's what our data looks like. Now, again, in the spirit of keeping things modular and fast, all of this jugglery can be avoided. So let's see how we can basically change our code. You see that here we calculated the sum, then divided it by count. This was not really necessary. Instead of sum, I can just call it mean, and then this becomes my average salary for title. Of course, that as type int I've already done, so this should work. And then I can completely get rid of this line. So I have that, and then again I get the same plot. So this works. Well, one of the other things we could straight away do is use the group by statement. What we are doing is, we have covered, by the way, group by and aggregation in one of the earlier videos. What we are going to do is, we are going to take India and we are going to group it by the Q5 column. What this means is that it's going to group the entire data set by each unique value present in the Q5 column. Out of that, those groups, we are going to select the salary min column. We are going to convert it into an integer, and then we are going to simply take the mean of it. So that's how group by and aggregation works. And there is a problem. Okay, so apparently you cannot access callable attribute as type. So let's do something else. We'll just convert smin into an integer beforehand. So it's basically not letting me convert integer types as part of the group by operation. So I'm just going to move the as type int outside, and I'm going to then calculate the grouped means of the salary column separately. So there we are. And we see we have more or less the same data. However, we can also plot this as a bar chart, and here we have it. So there it is. Of course, it's occurring a little weirdly. If I wanted to basically make this entire chart a little more readable, I would basically put this data in a variable called salaries. And then what I would do is, I would do sort values on salaries so that I get a nice readable chart like this where I go from low to high. And then I would basically do a plot. And there we have it. So yeah, this is a lot more readable. We see that product and project managers earn the most, data scientists on the second most, but you see that there is a big drop. So you see managers earn a lot more than most other people. You have research scientists, business analysts, who earn a fair amount of money, right? This is basically the order in which they go. Now you see that the people who earn the least amount of money in this whole thing are data analysts. But if you think about it really carefully, a business analyst and a data analyst are more or less the same thing. Now, this is a hack that you might want to learn from. Your job title really matters on your CV. So basically, if you are a data analyst, try to call yourself a business analyst wherever possible, because that alone seems to indicate a much higher minimum salary. And remember that we are still talking about SMIN. So these are the lower worst case scenarios. So to be very frank, business analysts and data analysts, they don't do things that are very widely different. They do things that are fairly similar to each other. So that is why, if I mean, the point is again that job titles matter, and precisely how they matter. Well, this is how they matter. This is basically the average salary of each job title that you have. Now, there are a lot of other columns present in the data set. You can look at them. There are columns that talk about education. So you can also repeat the same exercise and say what sort of education qualification earns the most salaries. What sort of software tools or expertise with certain software tools is likely to get you more salaries. Whatever. Does education correlate with titles? So how many data scientists have a PhD, for example? So you can do all sorts of these bivariate analysis combinations, and I encourage you to try them out. So that is broadly how you do univariate and bivariate analysis to tell stories with data. Essentially, here we have a clear-cut understanding of how salaries are reflected across multiple job titles. So do take a look on your own with more and more columns in the data set and try to see what you come up with.